Your car's speedometer reads 60 miles per hour. But hold on a second. You just started from a red light 3 seconds ago. How can you already be going 60 when you were just at 0? That's the fascinating thing about velocity. Today, we're going to dig into what really separates speed from velocity, why average velocity only gives us part of the story, and how instantaneous velocity lets us capture motion in the exact moment it happens. We'll also connect it all back to graphs and see how they unlock the hidden patterns in movement. Get ready to look at motion in a whole new way.
Quick pause. You're watching this because it was created on EulaIQ. EulaIQ instantly transforms your textbooks, PDFs, or notes into explainer videos, podcasts, or practice questions. Imagine turning your study materials into learning content you actually enjoy. That's what EulaIQ does, and you can try it now for free at EulaIQ.com.
Our goal is simple: to describe average velocity and acceleration, and to understand how velocity is different from speed. So let's start with a question that confuses a lot of students. What's the actual difference between speed and velocity? Speed is just a number. It's a scalar quantity. It only tells you how fast you're going. Velocity, on the other hand, is a vector. It gives you both how fast you're moving and the direction you're moving in. If your GPS says you're traveling 50 miles per hour northeast, that's velocity. If it just says 50 miles per hour, that's speed. And that directional detail becomes absolutely crucial when you're analyzing more complicated motion. Now let's pin down what we mean by average velocity. Average velocity is simply displacement divided by the time interval. We write it as v bar equals delta x over delta t. And notice, it's displacement, not distance. That difference means your average velocity can actually be 0, even when you've been moving the whole time. Imagine running around a track. You complete one full lap in 4 minutes. By the end, your displacement is 0 because you're back at your starting point. So average velocity is 0 divided by 4 minutes, 0 meters per second, even though you've been running the entire time. Let's work through another example. Suppose a car travels from position 10 meters to 50 meters in 8 seconds. The displacement is 50 minus 10, that's 40 meters. Average velocity is 40 divided by 8, which gives us 5 meters per second in the positive direction. But here's the interesting part. What if the car had taken a detour? Maybe it backed up first, then went forward again to end up at the same final position. The displacement is still 40 meters, so the average velocity is still 5 meters per second. And this points us straight at the limitation of averages. Average velocity can't tell us what actually happened during the trip. Did the car move smoothly? Did it accelerate, stop, or even pause for coffee? Average velocity treats all those scenarios exactly the same. It's like saying your average test score is 85%. That could mean you scored 85 on every single test, or it could mean you failed half and aced the others. The average alone doesn't tell the full story. This is why we need instantaneous velocity. Instantaneous velocity is the velocity at one specific moment in time, the thing your speedometer is really measuring. Mathematically, it's the limit of average velocity as the time interval gets smaller and smaller. Think of it like this. Calculate average velocity over 1 second, then shrink that down to half a second, then 1/10 of a second. As the interval approaches 0, the value you're approaching is the instantaneous velocity. The best way to see this is with graphs. On a position versus time graph, average velocity is the slope of a straight line that connects 2 points. Instantaneous velocity is the slope of the tangent line at just 1 point. As you bring those 2 points together, the line between them starts to look more and more like the tangent. Eventually, as the time interval vanishes, that line is the tangent itself. And that tangent gives you the exact rate of change at that instant. It's just like zooming in on a curve until it looks straight. Now, position time graphs are incredibly powerful once you know how to read them. A flat horizontal line means the object isn't moving at all, zero velocity. A straight slanted line means constant velocity, and the steeper the line, the faster the object is moving. If the line curves upward, velocity is increasing. If it curves downward, velocity is decreasing. And the sign of the slope tells you the direction of motion. Velocity time graphs give us even more insight. In these graphs, velocity is on the vertical axis and time is on the horizontal. A horizontal line means constant velocity. A slanted line means constant acceleration because velocity is changing at a steady rate. And here's the key. The area under a velocity time graph gives you displacement. That connection between the shape of the graph and the real-world distance traveled is one of the most powerful tools in physics. It transforms what looks like abstract math into concrete understanding of motion. So let's consolidate what we've learned. Speed is a scalar, just the magnitude. Velocity is a vector. It has both magnitude and direction. Average velocity is displacement over a time interval. Instantaneous velocity is the limit as the time interval shrinks to 0. And graphs, both position time and velocity time, reveal the hidden patterns behind motion. In our next video, we'll dive into acceleration, the rate at which velocity changes. And we'll see why acceleration and velocity can sometimes even point in opposite directions. Because motion is never just about changing position. It's a dance between displacement, velocity, and time. See you next time.
Before you go, here's the best part. This video wasn't handmade. I just uploaded a PDF and EulaIQ turned it into this explainer automatically. You can do the same with your own notes or textbooks, and in seconds get a clear video, an audio lesson, even quizzes. Start for free today at EulaIQ.com and make studying effortless.